Today we are walking through ATLAS Agent. I see your latent visual reasoning. One word is enough for both.
What is the central idea?
The paper studies visual reasoning. ATLAS tries to make those steps compact. Instead of drawing full intermediate images, culling tools, or adding hidden continuous states, it lets one ordinary generated token stand for a visual operation.
So the model is still generating tokens, but some tokens act like visual actions.
Exactly. A functional token is still part of the tokenizer vocabulary, so training can use the same next-step-down prediction machinery. But semantically, tokens like shape, arrow, line, text, and manipulation point to internal visual operations.
Why was that design needed?
The paper separates three earlier directions. Unified image generation approaches can produce intermediate visual states, but that makes training expensive. Agent IC approaches can call coder tools, but they take context switching latency. Latent approaches put reasoning into hidden embeddings. But the paper says they are harder to generalize and harder to train in parallel with autogessive generation.
What is the comparison in this diagram asking us to notice?
The bottom row is the proposed compromise. ATLAS keeps the efficient token stream of a language model, but inserts sparse functional tokens where visual work is needed. The paper's claim is that this avoids verbose intermediate image generation while keeping the training path native to standard supervised fine-tuning and reinforcement learning.
How does that look inside one answer?
This pipeline shows a geometry question. The model writes normal words, then emits a functional token such as line when it wants to add auxiliary lines, or text when it wants to label a pointer length. The imagined visual state is internal. The output sequence remains a single chain of tokens.
What makes the token sequence compatible with the existing model vocabulary?
The vocabulary is expanded rather than redesigned. It contains ordinary text tokens, the model's existing special tokens, and the new functional tokens. That means the model can predict a visual operation token with the same next-step-down mechanism it already uses for words.
So the equation is defining which token families can appear in the output.
Yes. The first line defines the whole vocabulary as the union of text, special, and functional tokens. The second line names the functional token set. The reason the paper writes it this way is to show that visual operations are not outside calls. They are first-class tokens in the same generation process.
How does the model learn when to use those visual operation tokens?
Training has two stages. First, the authors build ATLAS 178K for supervised fine-tuning. So the model sees reasoning trajectories where functional tokens appear in useful places. They also include perception data without functional tokens to reduce forgetting of low-level visual understanding.
And the second stage is reinforcement learning.
Right. The paper applies GARPO with rewards for answer accuracy, functional token usage when the final answer is correct, and format adherence. It also penalizes overly long or spammy outputs, because a model could otherwise game the token mechanism.
Why add a GARPO on top of standard GARPO?
Functional tokens are sparse. In standard GARPO, the sequence level advantage is spread across all generated tokens, so the few visual operation tokens may receive weak learning signals. LAGARPO anchors an auxiliary token level objective directly at functional token positions.
What changes between the left and right sides?
On the left, the advantage signal is broad, so the visual operation subset gets weak updates. On the right, LAGARPO adds the auxiliary loss only around functional token positions, making those updates stronger while retaining the normal sequence level reward objective.
What did they evaluate?
They use QN to 0.5 EL7B as the base model. The evaluation covers visual reasoning benchmarks including V-star, VLINK, and WeMath, with automated parsing under deterministic judge to verify answer correctness and format.
What is the clearest quantitative result?
The strongest number highlighted in the extracted text is on VLINK. The base QN to 0.5 EL model reaches 20.8% average accuracy. That is a large gain on a benchmark designed for structured visual reasoning.
Do the qualitative examples show the functional tokens doing real work?
Yes. In these examples, shape is used to localize a relevant region. Manipulation improves visual clarity. Arrow points attention to extra evidence. And text supports counting or labeling. The important point is that the tokens are integrated into the answer, not appended as isolated markers.
Can you give one concrete reading of the examples on screen?
For the climber image, ATLAS first marks the area containing the logo, then applies a manipulation step to make the letters more legible before counting consonants. For the mirror and counter examples, the same pattern appears. Localize the relevant region, add labels or arrows, then answer.
What about the examples with multiple images?
Those show the same mechanism on comparison tasks. ATLAS marks the part of the scene that should stay fixed. Uses arrows to track perspective or environmental differences. And uses filtering when fine visual texture matters. The functional tokens are tied to the evidence the model needs for the final answer.
What limitations should a viewer keep in mind?
The paper's evidence supports the value of functional tokens in the tested visual reasoning benchmarks. But the approach still depends on constructing useful supervised trajectories and on reinforcement learning that correctly rewards meaningful token use. The method also tests a compact token vocabulary, so future work would need to show how broadly those operation types transfer.
So the contribution is not just a new token list.
That is the core takeaway. ATLAS treats a single generated word as both an agent IC operation and a latent visual reasoning unit, then trains that behavior with standard token-based machinery. If the idea scales, it offers a lighter way to give vision language models intermediate visual reasoning steps without leaving autodescriptive generation.